Okay, so we were looking at codecs. If you remember, last time I talked about constraint coding. So we talked about our work on constraint coding, but after that, a lot of paper has appeared, especially by Keys Imik has also written a couple of papers. And there is one lady in Singapore. She has done some work, and also obviously in US, especially in California, Silicon Valley, some people have done some good work. So I will try to cover some of the stuff, the important stuff from that. But for now, I will move to the other portions of the project. Now, in fact, in the projects part, I am also, I think, going to make a list of these different codec areas, like say constraint coding, right? Or Reed-Solomon based, or some other things, right? And then one can pick up. So out of so suppose somebody is looking at constraint coding, right? So which one is the best algorithm that we can implement, right? Rather than implementing everything when you implement in terms of team, right? Codec. So, we will provide set of papers and all those things, and we can have discussions. Of course, the class size is too big, so that we need to look at. Anyway, so today, first I am going to talk about, so obviously, as you know that, so I see, I go by the history, how things are happening. So as you know, so 2012 was the first paper, 2013 was the second paper, and awards was the third one. And immediately at the same time, many people started working in that area. And, Microsoft entered into this business, obviously quite quickly. Something around 14, 15, 14. I think they formed a group, and now they have a very well established, department. So in the Microsoft about DNA storage. Okay, a lot of people are working in this area in Microsoft. So they try to build the whole machine, right? So just like that, to automate, how do we demonstrate fully automated system? Okay, so I'm going to show you that and the codec what they have used here, there. It's a very simple thing, obviously, but it's just a demonstration that yeah, you can do everything automated, right? So there are certain different parts and so on. So this paper, I think, appeared in 2019. Yeah. So you see, it's still not very far. It's just 3 years old. And within 3 years, a lot of work has been done actually, even, all these different components. So we are looking at this codec business. So this table is obviously, having papers till 2018, right? So as you remember, we are looking at archival DNA storage. Now, certain things that you should be familiar. So there are two kind of densities that we talk about. One is net information density. If you want to, so what is net information density? Number of input information bits divided by number of bases in the resulting DNA strings after the codec implementation, right? Input divided by output, and that gives you net information density. The ideal thing will be, so when we design the codec, like, 2 bits to one ACGT symbol. So 00011011 can give you. So the best thing could be 2, right? But if you just assign like this, you will not be able to correct errors, right? This is a simple encoding, right? So net information density, close to 2 is very good, which has the ability of correcting errors and so on, right? So obviously that is a challenge. So this is the one thing. And other density is physical density. As you know that 1 gram of DNA can store 455 exabytes of data. And there the best result has been obtained by, this George Church again recently, right? January, that paper was published, January, February or something like that. Yeah. No, maybe March. I don't know. Month. Yeah. So there, it is close to 432 exabytes. First time physical demonstration of this density, right? So people are reaching towards the uh, best possible information density, both in terms of net information density and also in terms of physical density. So these two are the challenges that we need to keep in mind. Whenever we are designing codec, it should be such that we are trying to reach the best level, right, in terms of the information density. Now again, this picture I have taken, actually you see, a student like you in Eva in her bachelor thesis, BTP or something you can say, she has implemented, I mean, she looked at this automated system of Microsoft. Look at the codec there, which is a Hamming code, and she looked at the Reed-Solomon code and compared, and she's concluding that Reed-Solomon code is better. There are certain good aspects about the Hamming code, but and actually, if you want to go for the long data, it's only can correct single error. In Reed-Solomon code have flexibility of correcting many errors. That is obviously better. So that comparison, everything. So this thesis is available. You can just even type on the internet, or have given the link, right? By the way, all these slides are available in the lecture folder. I hope you will be able to find it, right? So now, this thesis in 2019, you see. So by that time, the literature was, so the important work is 2012, 13. Robert Grass paper, they looked at the Reed-Solomon code. It's a very, I would say that it's very complicated, not very complicated, but very lengthy or tedious procedure to convert data into DNA strings. Okay, so they use some sort of codon wheel and so on. I'll talk about it briefly, after some time. And then they use Reed-Solomon code as the inner coding, outer coding. Before that, I have to tell you more about the Reed-Solomon code. So that paper was interesting paper. So you see that the size of data that was demonstrated in Church was 0.65 MB, Goldman 0.75 MB, gross 0.03, it's 83 kilobyte only. So it's very, very small. And then, there are a couple of other works. So this reference, third one is again a little bit more sophisticated effort by the Microsoft. And you can see that the information density here, you see, 0.83, 0.33, 1. So obviously 1.72 is much better up till that point of time in 2019. And so average information density is something around 1.13. If you look at by that time, of course, now we have very close to 2. Okay. And so there are some of the methods which are here also rewritable stuff they talked about, apart from archival. So, but I have taken this table. It's a good table to summarize everything, from that thesis actually to show you. So actually, this is the paper by Microsoft people where they talked about, so information density is 1.25 nucleotides per bit. And there they have demonstrated the automated DNA system, okay? So in another comparison table, you see that from all these papers, so RA means random access. So Church, any of these first 3 papers don't have random access. That is the thing, archival purpose. This Yazdi et al., that paper in 2015 is random access. Okay, so there and the method of robust system is different. In fact, I would say that this paper was pretty good actually. I'm going to talk about this paper in detail. Fountain codes. What are those? This paper appeared in 2017, and actually the codec of Fountain code was kind of motivated the Yin-Yang codec, which was achieved 432 exabytes of data. So in the George Church paper. So this is something pretty important one. Obviously, probably I will not cover all of them, but some of them, which are important ones now from the perspective of demonstration. So we have 1, 2, 3. So 1, 2, 3, 4 of them are random access, right? And in terms of recovery, where it is possible and not, okay, and the error correction detection, that capability. So the first one was obviously Church was having no error correction capability. Okay, so this is a summary. Okay, so these are the references I have given. So maybe you can look at it. I also taken again from that. So all those papers, 15 papers are listed here. Okay. So now first look at paper number. Which one is there? Yeah, the first one. Takashi, and so I think Karen is at Microsoft. She's leading all the efforts. So when they demonstrated this work in 2019, so let me show you that picture what they have done actually. Now we are working actually with them. In fact, for doing things. So now this is the paper. Demonstration of end-to-end automation of DNA data storage. You see, so 2019 they have demonstrated fully automated machine. Just for the demonstration purpose, they have used word hello. That's all. So encode using hello and decode it. It took them about 21 hours, do everything. So you see, it's a very, very early stage to demonstrate this thing. And so there are different components. As you can see, the storage unit, synthesis unit. This is all synthesizers because these are the the synthesizer system where you have A, T, C, G, and then combine them to give you the string of ACG, synthesizer. And of course, there is a encoder decoder. The codec they have used a Hamming code, which I am going to describe now. Actually, there are two things about sequencing and synthesizing. So as I mentioned, the best sequencing right now technique that is available is nanopore sequencing. I'll talk about it more when I'll discuss sequencing, different sequencing methods. Okay, so they have used it here. And also the synthesizer, they use enzyme-based, DNA synthesis, so which is also pretty good technology. So those are the best ones which they have used here. So we'll talk about the chemistry, how it works. Initially, I'm not discussing, otherwise people will be bored, right? So we'll talk about it anyway. But that's something very important, right? So this is the system. So let me show you how this Hamming business, Hamming codes that they have used in the Hamming codec. So Hamming codes, you already know. I have given you some idea about the Hamming codes, right? But I gave you idea over the binary field, right? And then you can do work on any query field with Q number of elements. You can construct Hamming code by constructing a petty check matrix such that no two columns are multiples of each other, right? Now, in fact, since I worked on Hamming codes in my PhD thesis, so what I did actually, rather than from field, I looked at the ring integer modulo 4 and look at the Hamming code. And again, I put the condition that no two columns are multiples of each other. And you can construct. So I've given a construction in my thesis actually, for the simplex and the Hamming code. Here, also they are using Z4 code, but a little bit different manner. They have given the presentation, so I'll show you that. So they have used, because they are just doing demonstration for hello word, that's all. So very specific Hamming code they used. Length 31 and dimension you can say is 26 because it's a free. Like there is identity matrix. See, the generator matrix is I26. Okay, so all these 26 rows will be independent, right? Even if forward Z4, right? Because there is identity matrix sitting there, right? So when you take the linear combination, total 4s4 26 vectors will be generated out of it, right? Anyway, and minus is, I mean, you remember we talked about from petty check matrix, you can get generator matrix and generator matrix to petty check matrix, and this minus a business was there. You remember? You can convert. So generator matrix is something like this, and petty check matrix is 31 by 5. So generator matrix is 26 cross 31, k cross n. Okay, and this is the A matrix that they have taken. The transpose is here written in this form. This is the petty check matrix. So basically, they are able to force this condition that because distance is 3, it can correct single bit error, right? That is what they have used. I mean, they have shown. So I think you need to probably, if you want, you can, of course, the Python code is available on their GitHub. If you want, you can check yourself the whole implementation, right? So what they have done, letter hello is converted into ASCII values, first of all, right? That is the main thing. And then you convert everything into base 4, 0, 1, 2, 3. Okay, 0, 1, 2, 3 they have taken for convenience because now 0, 1, 2, 3 can be converted into ACGT directly, right, with 4 symbols. Okay, so letter hello is converted into ASCII, ASCII is converted into base 4. Now, this gives you basically the hello message will be what? You combine, calculate them 1, 2, 2, 0, 1, 2, 1, 1, all everything. You have 20 quads. Quads means, you know, you are working over quaternary, right? 0, 1, 2, 3. Right. So this is basically a string of 20 length. Okay. Just calculate this. Now what? So all of you have done cryptography course, right? So you must be remembering what is known as SHA. SHA 256. If you remember, I don't know if you remember it or not. So first of all, what they have done is step 2. They add CRC, cyclic redundancy check, in the form of this hash function, you know, SHA 256 algorithm, secure hash algorithm. So what they have done basically, they computed that hash that turns out to be 110213, which they append towards the end. 20 plus 6, 26 size now. Okay. The whole string, you compute the hash, attach it towards the end. Okay. Now then what do? So now if you have 26, you know, remember k is 26 there in the generator matrix. So you multiply this vector with generator matrix to get 31 bits, right? I mean 31 quads. So basically you get something like this, 31 quads. When you multiply with generator matrix, this is the thing, right? Got it? Now once you got this, again a parity check is added at the beginning of this message. So what you do, so normally parity check in the binary code is just sum of the bits, right? You know, which is modulo 2 you can compute, right? So parity, even parity or odd parity will come. Now here actually it's because over Z4, so you just, you know, sum them and reduce it to modulo 4 and, you know, you get some parity. So basically, one bit, this parity turns out to be 3 here. Okay. And so that 3 is appended at the beginning. Okay. So this is how you get 32. So 26, so first it was 20, then 6 quads for CRC, hash function that computed, and then what? Yeah, then you multiply with the generator matrix, okay, and then you get 31, then you add a parity check bit, okay. So we are just using these additional things so that we make sure that if bit errors are there, you can correct it. And then final step is just convert 0 becomes A, 1 becomes C, and so on, get a string of ACGT. Now, can you observe by looking at this, this is the real thing what they have done. Hello is converted into this string. Is there any problem in the string? Yeah, so you look at this CCC is appearing 3 times, right? Why do you think that they still allowed this thing? Actually, they have observed that if 3 repetitions are allowed of AA, CC, GG, D, still there is no problem. So, okay, more than 3 is more severe problem, right? So, see, so in theory we do something, but in practice things are a little bit different sometimes. So even 3 is okay. Okay. Obviously, if it is no repetitions, very good. But even 3 repetitions is okay. You know, more than 3 causes more errors. You know, that is the thing. Okay. So even if they have done it and they have demonstrated, right, everything was done automatically. They have done the whole thing, working fine. As an engineer, it's okay. Everything is working fine, right? I'm not worrying about mathematics, but I'm just showing that everything is working fine, right? So this is the thing. So now I think obviously then the decoding parts I am not discussing, but it will go as usual, right? So this vector is stored, and when you retrieve it, some error will happen, right? So you remember Hamming code? How do you correct the errors? Just compute the syndrome, right? And the syndrome will give you position of the column where the error is, and you change that bit, right? So similar kind of things are there, which probably you can look at. I think it's very beautiful described in this thesis. Rather than discussing the whole thesis, I mean, you can look at it. I'll put all this material and put it in the lecture folder so you can look at it, right? So if the errors is going to happen. So I'll show you an example scenario actually. In her thesis, she has done the simulations also, and just implementing the BTech. That's the thing. So when no errors, you see D bar is so D is sent, D bar is received kind of thing, right? Then you can construct C out of it. Then B error type is 0. There is no error, and then whole thing message can be retrieved. Okay, one error. So then again, things can be handled. Two errors. So you basically code the too many errors made, and then because two errors cannot be corrected by Hamming code anyway, right? Single error can be corrected, right? No error or error. So I think so. Decoding part I am not discussing, but certainly you can look at the thesis. Very nicely described in the thesis, right? The decoding step as well. Just reverse of everything, right? Compute the syndrome, look at the position, and do the whole decoding. Okay. So I think that's all about Hamming. Okay. So now I need to talk about Reed-Solomon codes. Now, because for the Robert Grass paper, where they've used two Reed-Solomon codes, inner and outer, and there are a couple of other nice work where people have implemented Reed-Solomon code. So what I'm going to do, build little bit machinery for a Reed-Solomon code, because many people don't understand so easily, because it involves minimal polynomial, primitive polynomial, all those kind of machinery. So what is primitive polynomial and so on. So let me give you some brief idea about it, and then we'll talk about the examples and the constructions, and then Okay. So I will keep the discussion to be minimal. So you remember a finite field GFQ was something like 0, 1, alpha 2, alpha q minus 2, right? So this is built from GP. So Q is P raised to power M or something, right? In general, finite field is built from ground field. So you look at a irreducible polynomial over ZP, which has no root in the ground field, right? Attach that polynomial and then construct the field, right? In the powers of alpha, you can actually construct everything in the form of powers of alpha. Now, some of the properties that I would like to mention here. Suppose beta is a non-zero element of GFQ. We can define what is known as order of beta. Order of beta is the smallest positive integer m such that beta raised to power m is equal to 1. So beta into beta into beta, you multiply, minimum number of times multiplication should give you 1, right? So that is known as order of that element of the finite field. Okay. So let us take an example. If we take Z5, 0, 1, 2, 3, 4, right? So 1 raised to power 1 is 1. So 1 into 1 is obviously 1 raised to power 1 is 1. So order of 1 is 1. 2 square is 2. 2 square is 4, right? And 2 cube is what? 3. 2 raised to power 4 is what? 1, right? So order of 2 is what? 4, right? Similarly, you can see that order of 3 is 4 and order of 4 is 2. So we can compute order for every element, right? 1 into, all non-zero elements. I'm just multiplying 2 square, 2 cube, 2, 3, 2 raised to power 4. So we are getting, so order of 2 is 4. Order of 3 is also 4. You can compute like 3, 3 square, 3 cube, and so on, right? 3 is power 4. And order of 4 is 2. So what you observe that 3 and 2 are special, right? They are having order less than 1. So whatever is the size of the field, less than 1, right? So basically, they are generating the whole thing except 0, right? So these are known as primitive elements, okay? Primitive elements. So 2 and 3 are known as primitive elements. PE, primitive elements, right? So actually, you can also see that. So finite field has this property. If you look at all non-zero element and make a table of multiplication, so actually it's a group. Okay, and there are generators. For example, 1, 2, 3, 4. You can make a table, and you can see that the generators are 2 and 3, which will generate the whole group, right? But just keep on multiplying, you will get the whole group with respect to multiplication, right? So these are multiplicative group. So non-zero elements of the finite field forms a multiplicative group, right? All the properties are there, right? And so if you take any element in the field, its order will divide the order of the multiplicative group, which is q minus 1, because 0 is not there. Whole field has q number of elements. 0, you delete 0, so you get q minus 1 elements. So any elements, you remember in group theory, I don't know whether you might be in T group theory, the order of elements divides the order of the group. The order of the element here, so if it is m or whatever, so will divide the order of q minus 1, right? So order that is q minus 1. It will always divide q minus 1. Also, so basically, what are primitive elements? All elements of the field which has order q minus 1 are known as primitive element. Okay. Yes. Huh? Order of element divides the order of the group. 4. So here 4. Ah, 2 divides 4. So whatever the individual elements, if you compute their order, it will divide the order of the whole group. So group we are talking in terms of you delete 0 and look at it with respect to the multiplication. Okay. So that is the order of q minus 1, because q minus 1 elements will be there, right? So that means there are elements. So key thing is that in this finite field, there are elements of order q minus 1. And these elements are very important elements. They are known as primitive elements. Primitive element. That's something you should put in your mind. Primitive elements. Each finite field has one or more elements which are known as primitive elements. Okay. Now, in fact, there is a nice formula that the number of elements in GFQ of order T is phi of T. You know what is phi? Euler-Torsion function. I think you might be remembering, Euler-Torsion function. So you know that phi of 10 is 4, right? Or I can define phi of T as T where P is a prime. Right? So phi of 6 is phi of 2 into 3, which is 2. Right? Phi of 15 is 18. So all elements less than this and which has GCD1, right? You can count. So this is Euler-Toshan function. This is very important, right? Now I think I should tell you something about some properties. If so, how many primitive elements are there basically in GFQ? Number of primitive elements are exactly y of q minus 1. Okay, so now you can verify this formula obviously. So in the Z5 case, we have two primitive elements, right? Of course, all these things require proof and thinking. I'm not going with all those things, but just mentioning the result. How many primitive elements are there? Okay. Now, if I take, so this was an example where actually, we talked about integer modulo 5. If I take some non-trivial field like GF16, 2 to the power 4, right? So there you know that everything can be written as a power of alpha, right? 0, 1, alpha, alpha square, up to what this will go? Alpha raised to power 15, right? Or 14? 14, right? So now, where alpha is the root of some alpha is the root of the polynomial pi of x is equal to, so 1 plus x raised to power 4, right? So alpha raised to power 4 plus alpha plus 1 is equal to 0. This is for field with 16 number of elements. We can construct the field using this polynomial and so on. Everything is there. Now, out of these elements, I mean, as I mentioned, pi of q minus 1. So q minus 1 is what? Pi of 15. What is that value? Huh? 8. So 8 elements will be there, primitive elements in this field, right? So as an example, you can see that alpha, alpha square, and alpha raised to power 4 are primitive elements. So just verify actually. Okay, alpha, alpha square, whereas alpha cube and alpha raised to power 5 are not. Okay, so I think that is, I leave it for you to verify. Now I am going to define a primitive polynomial PP. A primitive polynomial is a polynomial having primitive element as its root. Okay, so that polynomial will be called as primitive polynomial. Now I'll show you examples, actually some more detailed examples. Okay, so this is the stuff. So let me show you. I'm going to use, because who is going to type everything, I'm going to use some slides by Professor Arun Gulliver actually, where the list is given. Of course, one can use any other table also. So you remember that any field will have power representation, polynomial representation, and this kind of binary representation, right? Integer representation. Okay. Now this polynomial, you know, x cube plus x plus 1, as I mentioned, alpha, alpha square, alpha raised to power 4 are primitive elements, right? Oh, okay. Yeah, so of course, these are primitive elements for GF8. I'm talking about GF8 now. So this is the polynomial which one can use to generate the whole field, right? So if you remember, you know, I think in the discrete math class, we talked about GF8. There were two polynomials which can work. One is x cube plus x plus 1. Another one was x cube plus x square plus 1. Both are primitive polynomials. Okay. So the roots are primitive elements. Okay. And you can easily see that. So whatever the roots are, alpha, alpha square, alpha raised to power 4, if you multiply everything and do the calculation based on that polynomial, you arrive at x cube plus x plus 1. Right. So that calculation is possible, right? Okay. Both for field with 8 number of elements. And one important thing, if alpha is a primitive element, so its inverse is also primitive element. Alpha inverse in that surrounding of the field. So now basically if alpha is a root primitive element, so alpha raised to -1 is alpha raised to 6, alpha raised to -2 is alpha raised to 5, alpha raised to -4 is alpha cube, right? Because this is field with 8 number of elements. So that means alpha raised to 7 is 1. Right. So we can compute everything. So now if you multiply these things, you see you get the other polynomial, x cube plus x square plus 1. There were two primitive polynomials. One was coming from alpha, alpha square, alpha raised to power 4. The other primitive polynomial was coming from inverse of the roots, right? And then you form the polynomial and you are getting, you see, either one of will give you other, right? If you use this one, you will get that one, and that you use that one, you will get this one, right? Beautiful connection, right? So this is the, you know, another important result. If Px is a primitive polynomial, so is this polynomial P star x, known as reciprocal polynomial. X raised to power m times P raised to power x inverse. P of x inverse, right? This is also primitive. Yeah. Huh? Actually, there could be many irreducible polynomials. So primitive polynomials are irreducible, fine. I'll show you a list. There are polynomials which are reducible but not primitive. Okay, I'll show you that also. So I hope this is clear, right? The connection between so basically once we have the primitive elements in the field, you can form the primitive polynomial. So or you factorize the primitive polynomial, you will get primitive elements. The order will be q minus 1 for all of these points. And by the way, yeah, that's another thing. Number of primitive polynomials of degree m over a finite field is phi of q minus 1 divided by m. All these are interesting, beautiful formulas. If you try to prove them, it's a beautiful mathematics, right? So you can compute all this. Okay, so this is all about GF16, so on. Okay, so now I guess I would also talk about look at this GF8 example. So I'll show you how to actually arrive at this kind of calculation. So given any field, you can do this kind of decomposition. So this is known as conjugacy classes, right? I mean, you can see that alpha, alpha square, alpha raised to power 4 are one set of roots, and the inverse is this, right? Which gives you corresponding polynomials, right? So these two are the primitive polynomials. Both are irreducible, and these are also irreducible. I mean, but these are basically what I'm saying that minimal polynomial. So what is a minimal polynomial? Minimal polynomial is a polynomial of lowest degree. So minimal polynomial of alpha is the lowest degree polynomial having alpha as a root. Okay, that is known as minimal polynomial. Okay, so for example, this is also minimal polynomial of alpha. This is the minimal polynomial of alpha cube, because alpha cube is a root here, right? Or alpha is a root there. Okay. Okay, so this is the minimal polynomial of that element. Okay. So There are more, but the primitive polynomials are only these two. Okay, so now let me show you. Now, in case of GF16, right? Actually, I am writing order. You see that order of each of these elements. You can compute order for every element, right? These are the 16 elements of the field, right? So order, each element has order 15 here, order 5, order 3, order 15. Okay. So actually, if you want to find a primitive polynomial or these minimal polynomials, what essentially you want to actually have this kind of decomposition. Once you have this decomposition, you can actually calculate everything, right? So if you have suppose this decomposition, then you can form this polynomial, right? How? Because you know that if order is 15, which is q minus 1, these are primitive elements, right? So you just multiply x minus alpha into x minus alpha square into x minus alpha raised to power 4 into x minus alpha raised to power 8, and you will get a primitive polynomial, this one, right? So these two are primitive polynomials for 16, you can see that. And whereas these are, you know, so this is a minimal polynomial of alpha cube, this is a minimal polynomial of alpha raised to power 5, but they are not primitive polynomials. Got it? Very basic understanding. So just two examples I've shown you. I mean, you can construct as many as possible, right? So Reed-Solomon code as well as BCH code, they're all business of this primitive polynomial, okay? So people don't understand how to find primitive polynomial, first of all, right? And obviously, you know, so now we know how many of them are there and so on and so forth. You know, all the results are there, right? They are very, very useful. So basically, you know, in order to build the field, so basically you see the polynomials which are primitive can be used to construct the whole field, right? 16 elements, right? And that is true because that's how, you know, in case of Z5, you saw that 2 and 3 are the primitive elements and they can give you the whole group, right? Same idea here with respect to the polynomials, right? So this is what? Yeah. So this decomposition, so now the power of alpha, so 1, 2, 4, 8, 3, 6, 12, 9, 5, 10, 7, 14, 13, 11, all these powers of alpha, and that first one, the one is alpha raised to power 0. These are known as cyclotomic cosets. Yes. Thirteen, 11, 15. So they are separate, right? So basically, I should. Then you try, and that's an interesting thing. You can observe what happens, right? Okay, try. Actually, because the product, when you compute, it will not be a primitive polynomial. Actually, the product will not come as a primitive polynomial in that case, right? So another interesting thing, see. So all this alpha cube is the first root. Then alpha raised to power 6, 12, 9 are known as conjugates. Just like in the complex numbers, we have conjugate, right? So we have a plus ib, then a minus b is a conjugate. So here there are more conjugates. For each element, we have conjugates, right? So they are sort of connected to each other, right? That's why when we look at actually this power here, these powers are important for us, you know. So how do we get this decomposition of the power? Once you have the decomposition of the power, so that is known as cyclotomic cosets. Cyclotomic word is used, circle cutting. So, you know, there's some sort of circle cutting mechanism through which we can find these powers. Once you have the power, you can compute the, you know, you can just raise to the alpha raised to power that power, you get the whole decomposition. Once you have the decomposition, you can compute the order. So you know which one is primitive, which one is not primitive, right? And once you have that, you can construct the polynomials, right? And once you have the polynomial, you can do the whole thing, right? So this is a very, very important thing. So let me, so essentially, so cyclotomic cosets for G of 8 are these 0, 1, 2, 4, 3, 6, 5, G of 16, and G of 32 are these. So basically, I can just rate alpha raised to power 0 is 1. Right. The first case was trivial, which was 0. I am avoiding that, right? So rest is, and the one alpha raised to power 1, alpha square, alpha raised to power 4. Right. In the case of G of 8. And then alpha raised to power 3, alpha raised to power 6, alpha raised to power 5. Right. What? So this is the whole decomposition for. So now I will explain to you how to get this cyclotomic coset. Okay, and that will be enough for you to understand. By the way, I just want to mention that there is a cyclic Hamming code also you can form. So if you take, if Gx is a primitive polynomial of degree m over g of 2, so the ring of the polynomial g of 2x modulo gx. Gx is a primitive polynomial. Is the field of order 2 raised power m, because it's a primitive polynomial, it will generate the whole field, right? And if alpha is the root of gx, then these powers are the 2 raised power m elements of the field, right? All the elements of the field. That is the basic mechanism. Each element can also be represented by binary n tuple, which is fine. In fact, the Petri-Check matrix can be written as in this notation: 1 alpha alpha square alpha raised power 2 raised power m minus 2 for the Hamming code. You see, because each one you can write as a binary expansion, right, of those tuples, right? So now it's much more beautiful representation. And actually, so because of this nature, the idea of cyclic. So because these, so basically one can show that gx that these codes are cyclic, and hence you can construct the BCH code, which are another important motivation. We'll talk about it when we'll talk about the BCH code briefly, but that's all about this. And let me show you the basically cyclotomic cosets. Okay. So what you do, take set integer modulo p raised power m minus 1 multiply by p. So if you multiply by p the elements here, this divides z2 raised to power p raised to power m minus 1 into cosets. So, so cyclotomic coset containing S is S, T into S, E square into S, cube into S, e raised to power ms minus 1 into S, where ms is the smallest positive integer such that p raised to power ms into S is congruent to S modulo p raised to power m minus 1. So let us take, I want to find out what field with 16 number of elements. So I am taking p raised to power m minus 1, means modulo 15. Okay. And then, so p is equal to 2 here. Obviously, the first cyclotomic coset is C0, starting from 0, which is trivial. Then C1 is 1, the first element, S, which is 1, times P is 2, Then again multiply with 2 into 2 is 4. Everything is modulo 15 here. And 2 into 4 is 8. 8 into 2 is 16. Modulo 15 is 1. So we are done with this. So close this. And next, C. So 1, 2, 4, 8 is there. What is the next number? 3. Right? 3 is left. So we start with C3. Gives you 3, 6, 12. 3, 6, 12, 9. And after that, 27 modulo 15 will be 3, 6, 12, 9, right? Yeah. C5. 4 is there. 5 and 10. And then we are left with C7. 7, 14, 13, 11. So I think these are all with respect to modulo 15. So you can just try to do it for, say, G of 8, which is easy, right? You can see that. So 1, 2, 4 with the one of them, right? So I hope so. This is how you get the cyclotomic coset, right? You just take element 1 and then multiply with 2 and then get until you get the first element, right? You keep on multiplying. powers. So once you get this, they can raise the power alpha, and then you can get the whole decomposition. So you can get minimal polynomial and all those business, right? The minimal polynomial, right? Reducible polynomial. So I think that's all. So the next class, now then we will be able to now describe the Reed-Solomon code, and then we'll see how the codec is designed. Okay. Thanks.